So, your last homework on chapter 7 is due on the 8th. The chapter 7 quiz will also be on the 8th in SI. Because you have SI on Monday, right? The last 2 Wednesdays for lab are makeup lab dates. If you have any labs you need to make up, I think most of you have your labs done, but you can check on Blackboard. On the 8th, we will do a review of chapters 5, 6, and 7 in lecture. And then on the 10th, we'll have exam number 3 on chapters 5, 6, and 7. Any questions? So we're going to finish chapter 7 today. We'll have a vote at the end of class today about what to do after, which will not be on the test, but it will be the lecture on Wednesday. Yeah, so that's the plan. So we were talking about lenses. The lenses consist of some material, and they bend light by refraction. Some material, plastic or glass, that refracts light waves to give an image of an object. They focus light by bending light through refraction instead of reflecting light like a curved mirror does. And because they have differently curved surfaces, that causes a net bend when light comes in and exits from refraction. So there are 2 main classes of lenses. There are converging or convex lenses, which are thicker at the center than the edge, and diverging or concave lenses, which are thicker at the edges than the center. So converging lenses with positive focal lengths look like this. Diverging lenses with negative focal lengths look like this. Now, when you have a converging lens, rays that come in parallel to a converging lens will focus at the focal point. With a diverging lens, rays that come in parallel to a lens will appear to have come from the focal point on the side that the rays were coming in. They're going to spread out like with a diverging mirror. If you have a convex lens with a focal length of 12 centimeters, you can draw ray diagrams for an object 18 centimeters from the lens. You draw a parallel ray into the lens, which then goes through the focal point, and then you draw a line through the center of the lens, and that'll meet. That's how you can draw ray diagrams. You can also use the thin lens formula, which is 1 over focal length is 1 over d object plus 1 over d image. F is focal length. It's positive for converging lenses, negative for diverging lenses. DO is the distance from the lens to the object. DI is the distance from the lens to the image. Negative distances mean a virtual image on the near side of a lens. The human eye consists of a lens, and the image focuses on your retina at the back of your eye. It will focus upside down because it's a real image focused on your retina. The brain will just properly orient it. Because the distance to the object varies and the distance to the image is fixed because your eye doesn't get longer and shorter. What has to change is the focal length of the lens. And you do that by squeezing or stretching the lens. The lens is flexible, and you have muscles that squeeze or stretch the lens, changing its shape, changing its focal length. The other way you can have an image with a lens and focus it at different distances is like what you do in a camera. A camera focus changes the object distance where the lens is fixed. So in a camera, what DO changes, F is fixed, so you have to change DI. And you can have, issues with your lens where you focus. You're going to be nearsighted or farsighted. That's when when you don't quite focus properly. You focus too short or you focus too far. So remember that light waves are transverse electromagnetic waves with both electric and magnetic field vectors. And so these electric field vectors can be aligned any which way. A given light source generally emits light waves that are randomly oriented, every which way. But they can be more or less aligned or linearly polarized like this. This is a polarizing filter. Let me just quickly check. What was it? This is currently, this way, we'll be filtering light, so only vertical polarized light can pass through. If I take another one, here's another one that's also vertical. Light just passes through. But I'll rotate this one. Vertical light is passing through this one. This one will only allow horizontal light through. And together, nothing goes through. But if I turn it like 45 degrees, some light makes through. So with a series of partially rotated ones, you can actually rotate polarization. And there are chemicals on, various molecules that will rotate polarization like that. Will cause polarization to rotate. A common one you may have heard of is sugar. Sugar water actually rotates the polarization of light you shine into it. But one that we use is that it turns out there are certain things, liquid crystals, that the amount they rotate the polarization can be affected by electric fields. That's how your LCD display works. It changes, it's got two polarized filters, and the amount it gets rotated depends on, that's the wrong tool, an electric charge placed around it, so you can change it from rotated far enough that it gets blocked, so it's dark, or so it makes it through, so it's light. So polarization is this preferential orientation of the field vectors. The polarization of light can be attained by several means, the most common of which is with a Polaroid film. These are Polaroid films. It's a film that polarizes. That is what the Polaroid company made before they made instant cameras. That's where their name comes from. And this type of polarizer only allows the components of waves in a specific plane to pass. It's basically a bunch of vertical lines. You're only allowed through if you line up with the slots. And the human eye has no way to detect polarization. There are animals that can detect polarization. Mantis shrimp, for example, can detect polarization, but humans don't. And when light is polarized, we can get extra information about it. So one of the things that was done with the Event Horizon Telescope is they studied the polarization of the radio waves they were collecting from around the black hole, because that told them about the magnetic fields, because that light is being created in magnetic fields, which can adjust that polarization.
What is polarization? Light bouncing off objects allows us to see them. Light is an oscillating electromagnetic wave. We see different frequencies of that oscillation as different colors. The electric field component of a light wave can oscillate in any direction perpendicular to the direction of travel. Light from the sun oscillates in all directions. We say it is unpolarized. If the waves have a preferred direction of oscillation, they are polarized. For example, light from your phone is vertically polarized. Your polarized sunglasses are a polarized filter. Here, they let vertical polarization through. If we rotate them, almost all the polarized light gets blocked. Light produced by a torch is unpolarized. When we place a polarized filter in between, the light becomes polarized. In space, randomly moving hot gas or plasma emits unpolarized light, like the torch. Plasma threaded by a magnetic field is ordered and the emitted light is polarized. The magnetic field acts as a polarized filter. The strong gravity near a black hole bends the magnetic field and twists the polarization direction of the light from the surrounding plasma. The polarized light rays that manage to escape travel to a distant camera. The intensity of the light rays and their direction are what we observe with the Event Horizon Telescope. Using this knowledge, we can map out the magnetic fields that surround black holes.
So that's one of the uses of polarization. You can use polarization to obtain information about various objects. If you want something that was, Dr. Lacani did work using polarization for spectroscopy. That involved circular polarization, I believe. I think he did VCD, which stands for vibrational circular dichromism, but that involves circularly polarized light. You could have up and down polarized light, linearly polarized, but it's possible to have light that's polarized so it's sort of spiraling along, and it can be spinning one way or spinning the other way. And yeah, so I think when he was doing his PhD work, he was working on VCD stuff, if I remember correctly. So if you have two polarizers that are aligned, they'll let through the polarized light, like I showed. If they're crossed, they will block. So here is a short video about those differences in polarization and showing you more or less what a polarized filter looks like at a large scale. And you can only polarize transverse waves, like light or a wave on a string. You can't polarize.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
And these Polaroid films are very much like the structure we saw that was polarizing the Slinky. There are a bunch of vertically aligned molecules that polarize the light, is my understanding. I don't fully know how they make polarizing films, but that's basically how it works, is my understanding. So polarization of light is an experimental proof that light is a transverse wave. Longitudinal waves like sound can't be polarized. And one of the reasons we use polarizing sunglasses is, well, one, cuts out half the light, but when light reflects off of a surface, it tends to be horizontally polarized. So when you get very sharp glare, you get bright reflective glare, that tends to be partially polarized in the horizontal direction. And these polarized reflections increase the intensity and are often seen as annoying or dangerous glare, reflecting off a road or a car or something. And these are particularly attenuated by polarized sunglasses, because the polarized sunglasses are vertically polarized, so they cut glare much more than all the other light. And thus, polarized sunglasses are oriented vertically. They don't allow the horizontal component of light to pass, and therefore they significantly reduce the glare. LCD screens also use polarization. I believe this is showing a 90-degree rotation, which is how the original LCD screens worked. Modern ones have a bigger rotation. It turns out that allows you to use less electricity to twist them. And so it's more efficient.
LCD screens are cool. But how do they work?
Liquid crystal displays, or LCD screens, are composed of millions of pixels which are made out of 3 smaller subpixels, each in control of one color, red, green, or blue. By changing the value of each subpixel, any color can be displayed. An LCD screen is made out of the backlight, horizontal and vertical polarizers, transparent electrodes, liquid crystals, and a screen, all working together so you can watch your favorite shows. The backlight emits both horizontal and vertical polarizing light, which passes through a filter, filtering only horizontal polarizing light. Now, as the name suggests, they use liquid crystals in order to change the value of every single subpixel. Depending on the color required, transparent electrodes will align liquid crystals to alter the filtered light, allowing it to pass through the second filter. The double filtered light finally hits the screen, producing a value for the subpixel. This value increases depending on how much light it receives, scaling from 0 to 255. This means that every pixel is controlled individually, making for precise displays.
LCD screens are truly incredible and fascinating. Thank you for watching.
Now, yeah, so that LCD screen description, that showed it going from 0 to 90 degrees. I think the modern ones actually go from like 180 to 270, because it turns out it's more efficient. It's the same idea. It's just there's some extra twist in there. Now, when waves hit a corner or pass around an object, they bend. So we're moving past an opening or an obstacle that has a size smaller than or equal to the wavelength, objects will bend. All waves, light, sound, light, water, etc., show this type of bending as they go through relatively small slits or pass by the corners of objects. And the larger the wavelength compared to the size of the opening of the object, the greater the diffraction. And you can experience this in general. You hear sound around corners, you don't see around corners. Light generally doesn't bend around, diffract around corners, but sound does, because the wavelengths of sound are much longer. They're on the same scale as like this dolphin, for example. So longer wavelengths diffract more. So here's an example of diffraction, and it's the ratio of the gap to the wavelength. So here we have the diffraction is greater as the slit is made smaller. This is hard to see. This got, let me make this white so it's easier to see. The background got messed up. So you can see the diffraction is bigger when the slit is smaller, because it bends more with a smaller slit. And so remember that sound has wavelengths on the scale of like centimeters to meters, where visible light has wavelengths of 400 to 700 nanometers, really small. And so noticeable diffraction readily occurs for sound waves, but yeah, we could hear sounds around the corner, but a beam of light on an object casts a shadow zone with a very sharp boundary because the wavelengths involved are much smaller. If you were looking at the wavelengths of like radio waves, they diffract. That's why, part of why AM radio goes around buildings better than FM radio, because it's got a longer wavelength. So I can demonstrate diffraction. Here I have a diffraction grating, like we used in lab. And a diffraction grating has a bunch of slits that are very small. I don't remember what the size of the slits is on these, but so you can see if I shine. I will shine this laser light. See, you can see through the diffraction grating, we get a nice pattern of red dots from my laser pointer, and they're spread out. If I switch to a shorter wavelength, you can see these are closer together than the red ones were. Actually, let me put this on a stand. So here you can see this is green. They're relatively short. If you do red, you can see the spacing is bigger. And then if I go to an even shorter wavelength, you can barely see this. Let me turn the lights on. There. These are even closer together. So the blue, this is green. You can see that's further apart than the blue. And lastly, the red is furthest apart. So the spacing depends on the wavelength, because the spacing of the slits is the same, but different wavelengths. Longer wavelengths bend more. So a beam of light on an object will create a sharp shadow. And if you look at close examination, you'll find the edge of a shadow is blurred or fuzzy. The blurred edge of a shadow is a result of light diffraction. And for example, in a movie theater, sound is easily diffracted around the person in front of you, but light is not. You need to bend around the person in front of you to see, but not to hear. Radio waves diffract. Radio waves are electromagnetic waves with very long wavelengths. AM have wavelengths of 180 to 570 meters. FM is 2.8 to 3.4 meters. Because AM waves are longer, they're more easily diffracted around buildings and other culture due to their longer wavelengths. So more diffraction leads to better reception of the AM bands in some cases, because they can go around buildings more easily than FM and other things. They go around structures and things more easily. And when two waves meet, they're said to interfere with each other. And the resulting waveform is a combination of the individual waves. When you combine diffraction with interference, you get those patterns I was showing. So the principle of superposition is that the combined waveform is given by the sum of the individual waves. And while interfering, it's possible for two waves to either reinforce or cancel each other out. And if you have constructive interference, that's when waves are lined up and they reinforce each other, causing the resulting amplitude to be bigger than each individual pulse. And destructive is when wave pulses tend to cancel each other out. And in both cases, interference can be total constructive or total destructive interference. And this destructive is misleading because the energy isn't destroyed. But here are some examples. Here we have constructive interference. The two pulses add up, creating an even bigger pulse. And here we have destructive interference. The two pulses cancel out, creating a smaller pulse. And if you've ever used like noise canceling headphones that are actual like active noise canceling headphones, they use destructive interference to cancel the noise. They play the noise upside down so it cancels out with the noise coming in from outside, so you don't hear that noise. And that interference is something we see in thin film. So if you've ever seen like an oil slick on water that's all rainbowy and colorful, or a bubble, a soap bubble, those are explained by interference. You have a thin film of oil or bubble, and you have reflections from the front side and the back side, and they can line up to add up together, or they can line up so that they cancel out. So part of the light is reflected at the air oil surface, part of the oil water surface, and part is transmitted at the oil water interface rather than reflected. And the reflected waves will constructively and destructively interfere depending on the angle of incidence, the angle of observation, and the thickness of the oil. So what you have is you have reflection off the oil and reflection off the water at the bottom of the oil. And if they're in phase for a certain wavelength, they'll add up and you'll see that color brightly. And if they're out of phase, they'll cancel out. You won't see that color, which is why you get these rainbows. There are also things in nature that use this sort of interference to generate their color. Most blues you see in nature, blue eyes actually, not that I have blue eyes, but also blue feathers on birds and on a lot of insect wings are actually structural color. They're caused by this interference. So a lot of butterflies, if you put like a drop of alcohol on their wings, the color goes away because it's all structural color. And when you put alcohol on it, you change all the way, change out all the interference works. Because there's like, and then when they dry, they're bad. But it changes how the interference works. It's also, but like it's surprising how many things are actually structural color. Blueberries, actually. Blueberries are purple with a blue layer of structural color, which is weird, but it's a thing that happens. So diffraction interference occurs due to the bending of light around the corners of a narrow slit. And if two narrow slits are employed, it's possible to compute the wavelength of light from the geometry of the experiment, like I was showing. And if multiple slits are used, sharp lines are produced that are useful in the analysis of light sources and other applications. So this has like a grid pattern, lots and lots of slits, but they're both horizontal and vertical. Which is why you get dots up and down and left and right. Well, you get this sort of square pattern. So each of these dots is an extra wavelength apart. So straight ahead in the middle, they've traveled the same distance. One to the left, it's traveled an extra wavelength. Two to the left, it's traveled 2 extra wavelengths, and so on. And that can be very useful in the analysis of light, because you can use a diffraction grating like this to split light up into various wavelengths, like we did in the lab. Here's an example of diffraction interference with just a single object. This is with a wire. Because you do get an interference pattern even with just a single slit or with a single wire. We've been talking about what is basically the double slit example, or the many slit with a diffraction grating. So this is a video about diffraction using laser.
This is a laser, and I can use it to demonstrate something that you've learned from a very young age, which is that light travels through space in straight lines. The laser is shining onto the screen. You can see the spot where it meets the screen, and I can make the laser beam visible by spraying some water mist into its path. You can see the beautifully straight path that it takes. Now, you've probably also heard that light travels through space as a wave, and I can use this laser to demonstrate why scientists believe that to be the case. Now, to do that, I need a wire. It's a thin wire. It's only 100 micrometers in diameter. The wire is held vertically between these 2 clamps. Now, I'm going to slide this wire into the path of the laser beam. Before I do that, I'd like you to predict what you expect to happen to this dot on the screen. Most people expect to see a shadow where the wire blocks some of the laser light. So if this represents the circle on the screen, then most people expect the wire to come in front of the spot and leave a shadow. Let's see what actually happens. You can see here where the light has hit the wire, and on the screen you can see, well, it's not a shadow. There's no line down the middle at all. In fact, that's the brightest part of the pattern. And coming out on either side, horizontally, we can see a pattern of bright and dark regions. So what's going on here? We can only explain this pattern if we understand that light travels through space as a wave. The light waves travel from the laser to the wire, and they're diffracted as they pass either side of the wire. That is, they're bent into the region behind the wire. Light waves which have travelled one way around the wire meet up with light waves which have travelled the other way around the wire, and they interfere with each other in the region between the wire and the screen. So let's take a look at this pattern in detail. In the centre, we can see there's a bright spot. There is no dark line. What's happening here is that light waves which have travelled around each side of the wire are arriving in step, that is, in phase. The wave crests add to each other, leading to constructive interference and a bright spot. If you move a little bit further out on the pattern, we reach a dark region. What's happening here is that the light waves which have come around one side of the wire are arriving exactly out of step, that is, out of phase with the light waves which have travelled around the other side of the wire. That leads to destructive interference. If we move a little bit further out, again we get constructive interference between the light waves which have travelled each way around the wire. And this pattern repeats as we go further out. Now, this is quite a simple demonstration to do, but the detailed explanation is really rather complicated. The key point to remember is that it's impossible to explain this kind of pattern without the idea that light travels through space as a wave.
So if you have two slits, you can work out like where you get bright spots and dark spots. And you can see the spacing of the bright spots and dark spots is different for different wavelengths. So that is in the center, the two light beams have traveled the same distance. The next bright strip is they traveled one extra wavelength. You can see how the bright strip for the red is further along than the blue, and so on. And for multiple slits, you get very sharp interference patterns compared to only two slits. This is very useful for separating light, like white light, out into its component colors. That's a diffraction gradient. Like I showed you here, though the diffraction gradients we have here are not so good for actually doing science because they do both vertical and horizontal, which is not ideal. You just want one direction. But, I mean, the ones in the spectrometers in the room across the hall work just fine. So, some important equations from chapter 7. The index of refraction is the speed of light in a vacuum over the speed of light in a medium. The bigger the index of refraction in the medium, the bigger the index of refraction, the slower light travels in that medium. For a spherical mirror, the focal length is half the radius. To find the location of an image for a mirror, 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Negative focal length is a diverging mirror. Positive focal length is a converging mirror. Diverging mirrors are the outside of the ball. They're convex. Converging mirrors are concave. Negative distance to the image is a virtual image on the far side of the mirror. To find the location of an image for the lens, 1 over focal length equals 1 over di plus 1 over do. Negative f is a diverging lens, which is thinner in the middle and thicker at the edges. Positive f is a converging lens, which is thicker in the middle and thinner at the edges. Negative di is a virtual image on the same side of the lens as the object. Because mirrors, you reflect, lenses you pass through. So the question is, what would you like me to cover on Wednesday this week? We have 4 options. I could go over chapter 8 on electricity and magnetism, chapter 9 on atomic physics, chapter 10 on nuclear physics, or chapter 11 on the chemical elements. This will not be on the test, but which one would you like to see? I'm hearing a 10. I got 10s. Let me see, what are you guys? Anything from you guys who are here remotely? Well, it looks like it's going to be 10. That's what people chose last time, so I'm not surprised. Yeah, so I'll talk about nuclear physics. That lecture won't be on the test, but I'll just go through the chapter. Any questions about anything? Well, that is the extent of what's going to be on the exam. We will get up through chapter 7, and we chapters 5, 6, and 7. We'll see you on Wednesday. Okay. Have a nice day. Share. Let me